Well, good afternoon, everybody. Thanks for coming by. Today, I'm going to touch base on different types of foaming agents, chemical foaming agents, their applications. I'm going to get into a little bit of the process, but each application is different, and so, different things may need to be done to optimize the foam and get you where you want to go. So, as you can see, I've got a lot of parts up here. Everything here is foamed, aesthetic, non-aesthetic, different foaming agents for each one. We do have a microfine cell for thin wall applications. I guess when you get into foaming agent, when you start talking about foam and what you want to use it for and what application you're going to need it in, there's really three types of chemical foaming agents. There's an exothermic, endo-exo, and endothermics. So everyone has their lane, so to speak. So in extrusion profile, exothermics tend to work the best, or maybe an endo-exo hybrid. When it comes to sheet extrusion, endothermics perform extremely well. And we do have samples of sheets and stuff right here that we're done with endothermics. Extrusion blow mold would be endothermic, injection molding, structural foam, low pressure machines. It's all endothermic foaming agents. Rotational molding would be an exothermic. So there's different applications. One thing stands true about all these applications is temperatures. Controlling the temperature gives you a consistent shot to shot. And what I mean by temperatures is foaming agent, it takes heat for foam to go off. And most of our products, until we get into our engineered grade for polycarbonate, nylon and those kind of applications, that product kicks off about 450 F. Most of the endothermics go off about 330, 320, right in there for olefins, styrenes, PVC, ethylenes, propylenes, TPEs, TPOs, TPUs. Acetal is a kind of a weird product, but exothermics work best in that application. I had to learn the hard way on that. So I kind of want to get into a little bit of the process and how to control the foam. If you're going to add this product, remember, heat makes it go off. And the hotter it is, the more active it gets. So a foaming agent in most all applications will reduce the viscosity of that material. So always think about, your heat reduces viscosity. The hotter it is, the lower the viscosity. But keep in mind that foaming agent does that as well. So you want to take advantage of foam. And what I've typically, when I typically do a trial, I'll go in and talk to people, I emphasize that viscosity change. That viscosity change is huge. You can drop temperatures. I've gone, I've gone from 20 to over 100 degrees off of barrel temperatures just by adding a chemical foaming agent. A lot of people, sometimes they get a little antsy about dropping those barrel temperatures, and we have to really do it to show them just how important that is. And that'll help control the bubble. So you don't get a lot of pre-foaming in the rear, and most of the product goes up front. When it comes to injection molding, temperatures and pressures are probably the most important. And then you get into, velocities. Faster you go, the better densities you get, the more foam you put in the middle of the part. Because foam, when you're talking about aesthetic parts, these high gloss parts, Class A surfaces, this is about a 10% weight reduction. So injection velocity is very important, because foam, when you're doing our microfine cell in a thin wall application, foam really doesn't want to come to the surface. It wants to go the least path of resistance, and that's right into the core. If you've got some ribs or some boss areas, things like that, that's where the foam naturally wants to go. And that velocity keeps most of the foam in the middle, and it doesn't push it to the outside. So if you start packing it, or you inject slow, it'll push that foam to the surface, and that's where you see splay. So speed is important, even if it's non-aesthetic. The faster you get it in, the better it is. Unless you've got, you know, I've foamed parts that, you know, they want the splay look. They do want a density reduction. They do want cycle, which foaming agent, as far as I'm concerned, endothermics, I always get cycle and weight. But they want that look, but the faster you inject it, like in a bin or a large structural foam part, you jack it in fast, you'll get swirls. It'll look kind of funny how it goes over ribs or goes over corners. I mean, there's a lot of turbulence going on there. So if you just want that real pretty look, nice even splay throughout the part, lower speeds makes that happen. I mean, it can give you right from the gate out just a beautiful splay that just flows really nice, and you don't have any turbulence. And because of the low pressure application, you take weight out. The cycle comes from the temperature reductions. And the endothermics, they do pull heat. We all know that. But the cycle, when you take that BTU out of that barrel, whether it's extrusion, injection molding, structural foam multi-nozzle, when you start pulling that heat out of that screw, that's a lot of energy reduction, and that's what helps with the cycle. BTU out of there means BTU out of the mold. So I'll talk about injection, then I'll move on to structural foam, then we'll talk a little bit about extrusion. So injection molding, again, speed is the thing to do. Rear zone's cooler, and the reason I like rear zone's cooler is that keeps the foam from pre-foaming in the rear. Now, really, you are going to lose gas. I mean, no matter what you do, you're going to lose gas. But you want to optimize that gas so you don't lose as much. So rear zone's cooler. Endothermics, they go off in a slope. You want your temperatures to reflect that. So, and then they talk about bell-shaped curves. My bell-shaped curve is going for top temperature at the head and then down at the die, or at the nozzle, and manifold systems. When you're talking about manifold systems and multi-cavitations, foam works extremely well in multi-cavitations. The important thing to remember is fillers, foam is a filler. You got talc, you got calcium, they're fillers. But talc and calcium, they don't go anywhere. No matter what you do in the process, you're always going to have that percentage of talc and calcium. But foaming agents are bubbles. So you have to be careful on how you treat that bubble. You can overpack it with slower velocities, too much pack pressure, and the bubbles are gone. So you want to be, there is a process to do all of this, but each application is different. I had an application where just recently it was polycarb, and they were running it and they weren't seeing any gas at all in the part, and they had the, you know, they lowered the rear zones, they kept everything really tight. Problem was there was too many shots in the barrel, so the gas was going up the hopper. They were getting a little bit, but not nearly enough. So basically what we did was we moved the shot size up, moved the transfer up to where you had a good size cushion that what it did is it just shortened the amount of time that one drop of material that goes through all these cycles and hits your mold, it shortens that amount of time to where it gets in front of that screw. And then that's when you can start foaming. That way, you know, you can actually capture more gas. And they see a whole lot of difference when they did that. So that's injection molding. I want to talk a little bit about residence time when it comes to injection molding. Some people, they choose screw delay and then zip it back. But what happens is as you delay it forward, material set drops on the screw, it sets there for your delay time. And that gas is going, and it's going right up out the hopper. So I recommend that you only use enough time to freeze the gate off, and then turn your RPM down to where it gets back just before the mold opens. Now I've had real fairly long cycles, and I've had to turn the screw down. It's almost like watching grass grow. I mean, it was really slow, but it would get back just before the mold opened. Now, all of a sudden, they were getting all this gas because everything was moving. It never set. You know, the only time it set was maybe for pack time or the mold opening. If it's a robot or whatever, the mold opening, mold closes, and it shoots. So you want to limit the amount of time the foam is just setting in that. And that's with just about any application. Extrusion's a different world, but any foam application, you do want to reduce that residence time. I've done tests where all I did was adjust the residence time, and I took an added pound out of the part. So that residence time, keeping it moving, no delay, no sitting there baking, that makes a huge difference in your process. I mean, even if you're running your temperatures a little warmer than what I would prefer, that residence time is going to make a big difference in what you're doing. So we'll get on to extrusion. If I forget anything, I might jump back. So, you know, bear with me. I've been foaming for, shoot, I bet 30 years, seeing just about every application. Had to manipulate the process a little bit just to make it work. But every application, again, is different. You know, how much of the screw you're using, what's the flow length, what's your temperatures, if it's multi-cavity, if it's single cavity, if it's valve gate, if it's hot tip. You know, people have problems with hot tip drooling, you know, and we can work around that. We can make that very doable. But multi-cavitations, you got to think that let's say you got an 8-cavity tool and you've got 2 parts that aren't filling very well, but the 6 cavities were filling like a dream. And you're getting all this foam in the 6 cavities, and you're getting foam in the short ones too. But when you start filling those short ones, you start overpacking the 6 other ones. Those 2 that you're trying to fill. So you can manipulate that with tip heats. You know, you can get around that, but again, balance is really important when it comes to foaming agent and injection molding. So we'll step over to extrusion a little bit. Extrusion is the ultimate low pressure. So when that material exits the die, it goes into ambient air. I mean, there's no pressure against it. What's nice about extrusion, you know, I do a lot of extrusion in sheet, in profile. Again, pressures mean a lot. So when you're doing extruder, you want to bring temperatures down because of the viscosity change. You want to build up the pressure, so that means screen packs. Typically on a 3.5 or 4-inch screw, I like to see about 22 to 2,500 psi pressure. And what that does is it keeps the foaming agent in solution, because under pressure, the foam can't expand. So you want to keep as much pressure on that screw as possible, so that you, and temperatures, so that you control that bubble when it, and that foam, to where when it hits that die, that's when you want it to expand. Now you're going to have, I can't even remember what they call that. I know it, but you're going to have things between the die and like a melt pump. You're going to have a melt pump. You're going to see a drop in pressure there, but not a tremendous drop in pressure. But there will be a drop in pressure, and it'll start to expand there too. But as far as sheet extrusion is concerned, you want the majority of the foam to expand right at the die. And when we talk about improving line speed and things like that, when the foamed material exits the die, it expands a little bit. So you got 2 options: either turn your RPM down or pull it a little bit faster. And our customers actually like to pull it a little bit faster. You know, they like the line speed, plus they like the density reduction. This is a ABA, and this is a softer material, mono layer. We can do mono. Mono layer is a little more difficult because you need to have that, you really need to control that bubble to where the surface is nice. And we do a lot of styrenics in that, and polyethylene, polypropylene. Thick, very thin. I've done blown film, 4.5% density out of a 0.69 mil trash bag. Caps, cups, bowls, you name it, we foam just about everything. Softer materials, TPEs, TPOs, TPUs. We're into wire and cable. We're into just about every market out there. Gas counter pressure, the different applications, core backing, over molding. We do big, small, tiny parts. It's the application is always different. I had a customer that was molding this little red part, and it was like an inch and a half screw. And the problem was he wasn't getting very much foam. So, and it was about the time it took for that foam, and it just went very quick through it. So, and I thought it was temperatures, but it really wasn't. What it turned out to be was it was going too fast through there. So we had to open up the cushion so that he had more time for the foam to go off in that cushion space. That's kind of thinking outside the box on a lot of things. So I look at parts. I really don't I don't work on your machines. I don't process on your molds. I understand foam. So when I go do a trial, I have a set of parameters that I look at to begin with, and that's temperatures and recovery time, velocities. I look at those to begin with, and then I look at the part and see how the part's reacting to these changes and see if there's any more changes. So if I see something going on with the foam, I'll go to the process engineer, process tech, and I'll try to explain what's going on so we can make the appropriate adjustments to get them where they want to be. That's the same with extrusion. I mean, it's tough to get guys to drop barrel temperatures in extrusion, but once they get it, they can do some amazing stuff in sheet and profile. But I guess, I don't think people understand how important that viscosity change is. So, and extrusion blow molding, I guess the key to that is temperature and pressure. And I'm talking about blow pressure. Blow pressure is like adding pack pressure. If you got it too high, it'll pack all the gas out of the sidewalls and you won't have anything. And as it comes out of the Parison, I mean, the viscosity changes. It is already changed. It's really easy to blow it out at that point. So keep in mind those pressures. Typically, I run about 30 to 35 PSI pressure. I've gone as high as 39, but if you're doing 40, 50, 60, up to 90, usually it's 90 PSI, you're not going to see anything. And frac melt polyethylene, I did a low density polyethylene and extrusion blow mold. It literally pushed all the foam to the edge because it was such a soft material. So, yeah, I'm still working on that. I love to be challenged with any application. It doesn't matter what it is. If you tried foam in the past, I implore you to rethink that, because there's a lot of stuff that can be done that nobody thinks about, and typically they're running too hot at temperatures when they could really run much cooler temperatures, still get the flow, and take advantage of that foaming agent. So rotational molding, that's pretty much exothermics. They tend to perform better than that. I've tried it with endothermics. Didn't work very well. Profile extrusion, same. I tried it with endothermics and I learned my lesson with that. Endos don't work. exothermics work the best. If it's flex PVC extrusion, and endothermic may work. I've had some success with that, but typically if you've got a shape or even pipe, you want to hold that dimension and you want to hold that nice round pipe, you got to have an azo. That's all there is to it, or a hybrid endo-exo. Either one will work just fine. All the parts up here these are static parts. They're lids, and these are all foamed. Every one of them are foamed. These bowls are foamed, and they've got a super high gloss surface. You don't even know the foam's in it. Same with these cups. Same with these hangers. And what we found really interesting with the hanger is, I don't know if any of you guys have had, I know I have plastic hangers, and they tend to break. And when they break, they got a big old hollow spot in it. And the knit line right down at the bottom here, it tends to not be very, very strong. So if you pull on it quite a bit, it'll snap. Well, with the foaming agent, because it flows, you got two cold fronts of no foam at all, it'll come in about like that, right? But when you add foam, it'll actually go a little bit further, and it'll lock in a little tighter. So your knit line right here tends to be a lot stronger. There's no voids in the part. Weight is achieved, and it's just solid all the way through. I mean, if you take and turn the color off of hangers that don't run foam, you'll see big voids. You'll see them up in the handle. You'll see them here. They're just everywhere on hangers. But a little bit of foam, don't take much. A little bit of foam will give you a much better hanger, along with cycle and weight. So people ask about, warp, and, a lot of questions about warp, in the years I've been doing this, and foaming agent will eliminate warp. I mean, it'll literally eliminate it if it's packed in stress. But if it's part design, the foam will help it, but it won't get rid of it. And the idea on warp, on a part that's designed or the part dimension is causing the part to twist or warp. The best remedy for that, is I strongly recommend foam, only because I can bring the temperatures down in that barrel, right? And put a lot less heat into that mold, and at your same cycle, your mold becomes almost like a cooling fixture, because it's a lot cooler going into the mold to begin with, and at the same cycle, it pulls a ton of heat out of it. So that'll help with warp as well. Non-cosmetics, pretty easy to do, squeeze and squirt, but I can tell you that just because there's splay on the surface doesn't mean it's foamed. It just means you got foam in it. So temperatures, injection velocity, whether it's non-aesthetic or aesthetic, very important that you get it in quick and get off of it. We get this tiny little piece right here, this little tube, and it's just loaded with bubbles. This thing was going so fast, I had to bring the temperatures up because it was going so fast in a small extruder that the foam just didn't have time to go off. It was crazy. So I went up like 25 degrees, but it didn't affect the temperature of the part. And that's what these guys were scratching their heads, how can you go up on these temperatures and yet not have that heat in the part? And the endothermics, again, they pull heat tremendously fast out of the part, and it cuts a lot easier. And even the tech guy said, I can't believe the part isn't a lot hotter, but it wasn't. So, and this is the kind of part that when it comes out to die, you got to run down the other end. That's how fast it's going, man. There's no stopping it. It's just chopping it like that, little pieces like that. It was just, it was amazing to do that. I have foam trash barrels, extrusion blow molded trash cans, and had cell structure going from all the way to the bottom, all the way up. Just beautiful. Injection molded trash cans. I think it takes like a 39-gallon trash bag. The cell structure in that and the part just looked amazing. They even had a high gloss area, no foam. It stayed right in the middle, and that was because of speed. I've done all kinds of trash cans, office trash cans, bale buckets, with it's a bucket that's got bales, a little spout on it. I mean, 2-cavity foam just loaded up in the walls. Now remember, when you're doing aesthetic molding, you can't expect a huge reduction in density. You're always going to get density. These are all aesthetic, and they got, of course, it was over molded with that. But in each one of these spots right here, you could take a jeweler's loupe and see the cell structure in the wall. This doesn't have a splay one, but it's loaded with bubbles. And of course they do this kind of molding. But I just wanted to show you what it looked like without that. And it is loaded with bubbles all the way up to the top. But again, you're only putting bubbles in the middle of a wall. So you can only expect to take it, that middle is only going to hold so many bubbles. And you start with adding more bubbles, they're going to make it to the surface and they're going to splay. So the amount of foam you put in, the velocity you use, that's going to determine, how much foam you can put in it, really. The faster you go, the more foam. And there's a certain point that no matter, you start adding foam and it'll start pushing it to the surface because you're really inundating it with bubbles. So you have to use the right amount you need to get where you want to be. And to be honest with you, I never recommend using more foam than you need. I've never done that. I only use the amount to get you to your goal or get you to as close a goal as we can, giving the parameters of the machine capabilities, and really every machine's different. So when I go into a specific challenge, I look at the machine and I work with the machine. Whatever the machine can give me, that's what I'm going to use, and I'm going to get you everything you can from that machine. I've been into trials where this machine is, injects at 3 inches per second. This one here injects at 7 inches per second. It's basically same size machines, but the difference will be the 7 inch per second machine is going to give me a lot better results than the 3 inch per second machine. So just machine capability is important, but don't think that we can't foam it because we can. Flow lengths is important as well. If you've got a big long flow length, that means you really need that velocity. Otherwise, by the time it gets all the way full, it's going to be pushing foam to the surface. The faster you inject it, the valley stays open, the foam migrates there. It doesn't want to go to the surface, but it can get pushed to the surface. So the longer the flow length, the more pressure you get to fill it. So you tend to push a lot of stuff to the surface, but that means lowering percent of foam and still running temperatures, recovery times, and low pressure. So I've molded about every material. I love challenges, and the reason I do is because I learn every time I do a trial run. If it's a challenging trial run, I take that information, and I work to work around processing issues. But again, I don't waste too many people's time at that. When someone calls me out to do a trial, or we're going to do a trial, I'm not going to sit there for 4 hours and try to make this product work if the machine can't do what I ask it to do. So I don't waste your time or mine, but I'm batting pretty good given an opportunity to foam anything you need to foam. I've done overmolding, both the cap, TPE cap, and the substrate. I foamed both same time, and it worked out really good. So do you guys, I mean, I'll pause for a second if you guys got any questions or anything. I've said a lot.
Yeah, can everybody hear me okay? Can we get a head nod from those guys that have some, perfect, thank you very much. Ron does not have an earpiece in, so we're reading the questions off to him.
I can read
you can read some of them.
Yeah.
Some of them also came in via private. So the first question that we have is, do you have foaming agents that are used with TPO, TPE for use in softening the parts?
No. Foaming agent might give it a little sponge, but foam is a filler. So typically when you run a filler, it'll add a little bit of rigidity. But if it's like a thicker TPE or TPO or TPU material, then that cell structure in the middle will make it a little more cushioning. But as far as the soft feel, you'll still get the feel of it. It'll give it a little bit of cushion. But again, it just depends on how thick it is and what you want to do with it.
Okay.
I wouldn't walk away from it. Let me put it to you that way. I mean, you always have to look at those things. You know, I've foamed them all, and I just got to talking to a guy that wants to foam something. There's soft material. He wants to foam it. He's not sure if he wants to use gas assist to kind of blow it up a little bit, or use foam. And I think the foam would be a little stiffer than that gas assist application, but I still think it'll give you a nice ride.
Thank you. Another one came in. What's your experience with bottle caps? And on the flip side of that, big injected parts, some larger parts.
Sure. I've done bottle caps, been very successful. High gloss surfaces, great cell structure. The bottle caps that we've done, I've done bottle caps for non-carbonated drinks, which is actually better. But for carbonated drinks, what's happened over the years is they've thinned out bottle caps. Everybody's thinned out their tools, and you know, at some point you can't really go any thinner. So then they start calling me, where is if you had an older bottle cap, I could take the weight out of it. I could make it, you know, for carbonated drinks. I could take the density out of it with a thicker cap and give you a really good part with the density reduction and the cycle. But they've thinned everything out so much that we've had it tested in carbonated drinks, and there's some tests that did good, some tests that didn't, so it just didn't work out. But caps in general, yeah, we can foam them beautifully.
Very good. Going back to some of our earlier questions as well, how does foaming agent impact fiber reinforcements? Do they cause issues with directional alignment and compaction?
Actually, when it comes to, you know, glass fibers and calcium and talc, as far as the alignment of the glass, I've never had any problem with that, but I do know that when you add foaming agent to any filled material, man, does it open the process window up. It does flow much better, and it foams really well with these materials. So, and I've done glass and talc and calcium, all of them. So when I foam, let's say a 30% or 40% glass, and I take 4% weight out of it, they kind of scratch their head and say, you know, this part is 4% lighter. You know, that's probably not enough. But you have to understand that if it's a 30% glass or talc or calcium, 30% of that part I can't foam. So when you're pulling 4% density out of the whole part, the material that costs the most, and that's your polycarb or nylon or polypropylene, that's what I'm reducing. So that 4% turns into a lot greater number when you consider that if it's 30% of any of those fillers, 70% is all you're going to be able to foam. 4% of 70% is if 70% was 100%, it would be quite a bit bigger than 4%. So foaming agent can only foam the polymer. It can't do anything with the fillers. But I haven't had any problems with glass. I foam a lot of glass material, polypropylene, long and short fibers. I've never had any problems with it. Hope that answers your question.
We'll find out. I'll keep going.
Okay, appreciate it.
You touched on this a little bit earlier, and that's probably why when this question came in. But if you can elaborate, what is the effect on shrinkage,
Yep.
excuse me, as well as warpage by
Yep.
using foaming
Well, the warp again, foam will help warp, and if you drop temperatures to pull the heat out of that, your mold becomes a warp fixture, and if it's packed in stress, we can virtually make a flat banana part. We can make it flat with a foaming agent. That it can do, but I know it can make it better when it's a design or the geometry of the part, but it typically won't eliminate it.
This one's going to be a two-parter. I'm going to ask.
Let me back up. I'm sorry. The shrink. Foaming agent is a filler, right? So it will reduce shrink. There's one application I ran. It was for a part underneath a motorcycle seat, and I fully foamed it. We had to speed it up 15 seconds to get it down to size because it was so big. So, foam will reduce shrink.
Good.
I'm sorry, go ahead.
You're fine, man. It's your show. This individual says, I'm interested to run a panel which is 8 inches wide, its profile, and about 1/4 inch thick with high impact polystyrene. Any information you can share on or elaborate about processing that with a foaming agent?
Yeah, yep. So styrene foams extremely well, right? It really does. And what we found is our foaming agents, we have pellets, we have powders, we have liquids. And what we're seeing in the sheet, and I've done, this wide to, 4 feet wide. What we found is the liquid foaming agent works tremendously well in that. Again, you control pressure, you control the temperatures, and if it's a mono layer, I don't know that if you're doing a mono or an ABA, but either way, a mono layer pressure to keep that pressure on the screw and temperatures, and you'll get a really nice, clean, very tight cell structured styrene part. And it does foam extremely well. Very tight cell structure. A lot of styrenes are vented. So when you're doing extrusion on parts, a lot of post-consumer, they dry it, things like that, or they have vents in their barrel. I do not recommend vents. You need to close them up, because if you have a vent, that foaming agent, it's gone. It'll go right out the vent and you won't have anything. So vents are really important when it comes to extrusion. Got to cap them off.
Cool. So to kind of piggyback on that panel question and profile, if that profile was capstock, would that change the foaming process at all? Does a capstock profile add any challenges to getting a nicely foamed center?
No, this part right here is capped, both at the bottom and the top. I'll come around here and see if you guys can see it. It is a really high gloss surface on both sides, and this is an ABA layer. And if you put a jeweler's loop to this, it's just absolutely loaded with bubbles.
Did you want to put it under the microscope?
Yeah, let me drop it under the microscope, see if we can get it. See if we can get a picture of it.
For those that are watching, it's the ID microscope. Go ahead and set it down.
Okay. Just run
I'll
it up
adjust it if you want to look up there on that screen. There we go.
Can you blow that up a little bit there?
That's on Carolyn's screen.
Yeah. That's cap stock, and it is loaded with bubbles. And I think that was around 20% reduction. Cap stock is clear, so you can kind of see through it, but you've got cell structure in the middle of it. And you may not be able to see that real good.
Is that any better with the light underneath it?
Yeah, that's a little better.
Let's try zooming in and getting that. There we go.
There we go. And if you look, in extrusion, when you get into extrusion, things like that, you're going to get a little bit of elongation, but the microfine cell, it's so small that the bubble is so small that it doesn't elongate like a typical foaming agent would be. You'd have a streak in it, you know, different streaks. As a matter of fact, when I did blown film with the microfine cell, I was surprised, but there was elongation, but it was really, really short for blowing it out so wide. So the closed cell bubble works really well in stretched material and things like that. But yeah, mono layers or again capped layers. Of course, you're adding material that doesn't have foam, but you're still going to hit a really good density reduction. And again, when it exits the die, it's going to expand a little bit. So you take advantage of that and run a little faster line speed.
Okay, kind of shifting directions just slightly. This participant is asking, is there any type of nozzle for injection molding that's commercially available in order to hold the pressure on the melt gas mixture and avoid premature foaming before injection inside the mold or not?
Right.
They want to be able to replace it with regular injection molding nozzle in the foaming process.
Right. So I think he's talking about shut-off nozzles that basically shut the material off. When you're doing, you know, big foam parts, thick 1/4 inch, you know, and just foaming it like crazy, which really what you want to do. We call that coming out of a nozzle drool. So you definitely want to, at that point, if you don't have a shut-off nozzle, it doesn't mean that it won't work. It just means you're going to have to bring that nozzle temperature quite a ways down. And remember, that nozzle just keeps the heat. It's not really supposed to heat up the material. It's supposed to maintain the material. And because the viscosity's changed so much, I've had parts where it would drool out. I'd start bringing the nozzle down, bringing the nozzle down, bringing the nozzle down, and pretty quick. And this is with our 5811. By the way, there's not a product out there that will outperform the 5811 in structural foam multi-nozzle or anything like that. They're just not. I've gone up against every one of them. But that being said, you bring that nozzle temperature down, and the mold will come out. If it's got a sprue in it, the mold will come out, and you won't have that drool because you're bringing those temperatures down. You hold it a little bit longer to settle things down. If it's a manifold system, you do the same thing with the tips, and you bring your manifold temperature down. If you got hot tips, you know, and a lot of times when you're trying to foam multi-cavities or you've got multi-gates, hot tips, I've had parts with 48 hot tips on them and drooling, but they needed a more aggressive foaming agent to pull weight out of this particular part. We turned the tips down, kept turning the tips down until there was just a tiny little pud on each gate. And shot to shot, it ran like a champ. So a shut-off nozzle works best if you can use it, but some people don't want that expense, so we can process around that and make it work.
Cool. Next question for some glass-filled nylon. Hollow rectangular shape extrusion profile. If they were to use foam, what will be the impact to the rigidity, long-term creep, impact, heat deflection properties?
Right.
The reason for using foam is for weight reduction. Also, hopefully we can improve those above properties. Again, what will be the impact to rigidity, long-term creep, impact, and heat deflection properties?
Right. Well, rigidity, the glass is going to do a lot about that. Now, foam will add a little bit. In some applications, I've added foam, and really, we know it got a little stiffer. We just, it's hard to measure because it is a filler. And, every time you're looking at, impact or anything like that, you got to kind of be aware of how much foam you put in it. Again, if it's extrusion, it would be probably an azo in that application, just to hold. I've done a lot of glass-filled applications for tests for creep, and it didn't seem to bother it a bit. So each application, each design, each part is different. But I'd like to try the foam in that and see what we can do, see how far we can go with it.
Okay. I think we hit a bit earlier on shrinkage and
Yep.
injection molding. So I'll let you elaborate on that a little bit later. But for now, moving on, do you have a foaming agent for PET? Obviously, those have some processing temperatures that are a little bit higher,
Yes.
280 C.
Yep. Yeah, we've done PET sheet. I think about, I don't know what it was, about 2 mil, maybe 5 mil. It's about that thick of PET. Took about 12% out of it. PET foams really well. It was difficult to talk these guys into dropping those barrel temperatures in PET, because in their minds that just doesn't seem right. But we did drop the barrel temperatures, actually quite a bit, and it foamed beautifully. So I think barrel temperatures is the key to high temperature applications. If it's injection molded, we got a 71896. It's our high temp foaming agent for nylon, polycarb, PET, PCABS, engineered grade materials that are hydroscopic. We don't recommend you dry this material with your resin. Of course, I wouldn't recommend you batch mix it with your resin and dry it. I mean, I would never recommend to do that. No matter if the foam could be dried with it, I would never recommend that. Because if you're dropping 0.5% or 1% or whatever percentage you're dropping, let's say easy math, 1%, 1 pound per 100 pounds of resin, you're not going to batch mix that to evenly disperse that into 100 pounds. So I always recommend auger feeding it. But yeah. We can foam PET. We can foam PET. I mean, PET foams really well.
Sorry, I forgot I was muted there for a second. So going back earlier to the paneling surfaces and profile extrusion, if we put a laminate finish on the panel surface, will the foam affect any adhesion of said laminate?
I don't believe it will. It's not going to affect anything on it. You're still going to have your polymer. As a matter of fact, when you cut the sheet open or the part open, you'll see that the foam is just in the middle. So you should have a wall both on the top and bottom. So that laminate is not going to affect anything on the foam. Or the foam's not going to affect it, excuse me.
Perfect. We did have a user that had to leave briefly and came back on, so I wanted to re-ask this question. Hopefully you can elaborate a little bit further. Do you have foaming agents that are used with TPO, TPE for use in softening the parts?
Yeah, so the only softening I think that you would get from that is the cell structure would allow it to, it won't be so solid. It'll be more of a cushy type feeling because of the cell structure in the middle. It won't be solid anymore. It'll have cell structure in the middle. So, it may give you a little more softness as far as, the pressure on it. it's not going to affect the softness of the material, you know, by the touch, but it may give you a little more cushion.
Thank you. And I actually missed one earlier, so I apologize to that participant. Do you have to change the depth and length of vents on tools when using foam?
The depth and length of what? Tools?
Vents.
Vents?
On tools.
Don't vent it at all. Don't vent it at all. If you have any vents in any application, extrusion or even injection molding, you're going to lose all the gas. You're just not going to get anything.
Okay. Another question. Can you foam POM?
Yes. Yes, that's Norel. Yeah. We can foam Norel. It foams extremely well. But again, with Norel, it's a hot temperature material. So temperatures mean a lot, but you know, when you get to engineered grade materials, you can't drop the temperatures as low as you can, like a polypropylene or a styrene or ethylene or things like that. But what's important is that recovery time and that residence time. You always want to keep that material moving. You don't want to leave it set back for a long time. You know, you don't want it sitting back there waiting for the mold, because you will lose a ton of gas. Just by that alone, just by slowing your RPM down alone, just that alone will make a huge difference in your product and how much gas you get into it.
You were talking about cups earlier.
Yep.
We overlooked this one. This is a question that had also come in. Why doesn't everyone in the cup business use a foaming agent?
I think a lot of them don't understand what the foam does. And again, when you're dealing with cups, you're dealing with multi-cavitations. And if you don't have a balance, what happens is you get cups with great cell structure, you get cups without great cell structure. So, and we've done a lot of cups, and they foam really well. It's just, I don't know why they don't want to do it. I mean, they foam really nice, but if you got a imbalance, then you're not going to get the same shot weight in each one or part weight, and you know, things are going to change. But as far as filling it and with low pressure, balancing, you know, making sure that you take advantage of that viscosity change, dropping temperatures, keeping the residence time down, you can get some great cell structure in cups.
Cool. Following back up on the TPE and TPOs, going back to the softening, do you have to have a moving core to allow the material to expand after being injected? They're specifically thinking about a part that is almost 1 inch thick where the foaming is happening. And how much density reduction have you seen in this type of application? So
you don't have to have a cavity or a clamp that moves or opens up while you're injecting. You don't have to have that. It'll foam. The thicker the part, actually, the easier it is to foam. And that just depends on how much you want to pull out too. A lot of times with soft materials, and they're thick, soft materials, you get it in really quick, you get off of it, and you run your standard cycle, and you open it up, and they start puffing up on you. Well, that's because the wall, and even if you lower the temperatures, it's a soft material. It's got internal pressure that foam's, you know, expanding inside, and it's taking up room. So sometimes a little longer cycle time fixes that. Maybe even a little cooler temperatures. It depends on what kind of surface you're looking for too, as far as mold temperatures. But you can take out anywhere, it just depends how fast you get it. You could take anywhere between 6 and 12% weight out.
Speaking of different things that you're adjusting with foaming, going back to that hollow rectangle glass-filled nylon, if they have limited flexibility in changing their temperature profiles, what else might you work with to adjust?
Well, can I ask right quick, that is an injection molded part?
Profile extrusion. Thank you. For
Okay.
that.
Profile extrusion. So if you got limited changes in temperature, if I remember that correctly,
Correct.
if nothing else, try to get the rear zones down, and you can deal with the rest of it. You know, you try to get the rear zones down. It'll make it, you know, you'll extrude it out, and it'll be, again, we'd probably have to test to see where you're at with the creep and all that other stuff. But I don't think that you're going to see much of an issue with that. I think your line speed will increase only because you can't change those temperatures as much. So lower amounts of foam will probably work better than higher amounts of foam. And of course, you're going to have to speed it up to get the gauge right. But it should be really consistent. And I don't think you're going to have a big issue with it unless it's really high pressure material. I've done PET pipe. I'm not PET pipe, but polyethylene pipe. Foamed it, looked great. They did a burst test. Well, the burst test didn't hold up very well. I mean, it held pretty good pressure, but it never reached what they typically do. So that didn't go over so well with them. But the more foam you put in anything, it's an additive. So the more foam you put in, the more you might affect the structural integrity of the part. So if you have a plus or minus on impact or any measurements you have, typically when someone runs, you know, they're looking at the impact, they'll do a high and a low. Everything in between there is spec, within spec. Typically they run upper to high on their spec. Well, we would not want to go out of spec. So we run only the amount of material that'll get you within spec, and probably from middle to lower is where we'd end up. So you would get some line speed and you would get some weight reduction still within your spec, your parameters. And a little bit of foam with not much control on temperatures, a little bit of foam goes a long way because it'll really start gassing up good.
Okay. Another one came in. What could be potential causes of burning when injection molding foam materials? They have a processor that believes foam is difficult without pulling a vacuum, which would be in disagreement with your comments about not venting a tool.
Right. You always want, maybe I misread the other one, but when it's injection molding foam, you want to vent it. More vents, the better. And
You're speaking of extrusion.
Oh, extrusion.
No, I'm saying that's what you were talking about earlier.
Yeah,
about
extrusion.
That.
Yeah, extrusion and injection molding, vented barrels and injection molding. I was talking about that, not so much the molds. But when you're talking about molds, you want to vent them as much as you can. Because remember, you're going to try to inject that faster. And I've got a cap here that on this side of the cap, and you can't see it, but I'll see if you can see it, but it kind of shows you what vents do to foam. I don't know if you can see it.
You may have put it under the microscope.
You see the lines going across there? I don't know if they can see that, how the foam is being just kind of moving up and down like that. The backside, here, we can put that on here. Show them this, and then show them the backside. And it's a great example of vents in a tool and what it does to the foam. The foam's flowing, right? So if there's a poor vent, it's actually going to add pressure to the foam. It's not going to push that air out of the mold. So it's literally going to pack the foam out as it's going to the end. And the other side of this cap, you got foam going all the way to the bottom. It looks great. But on the one side where you'll just see little waves like this going up in a little area like this, straight up, that's where the venting is a problem. So I don't know if you could back that off and show them a little better. You got the front side. You may not be able to. How are you looking at it from the side? You look at the bottom of the cap. What I'm trying to say is you don't want to look at that, Brian. It'll be right on the side here. But it's got little wavies, and that's the vent. As the plastic is flowing, that air is not venting out quick enough, so it's actually packing against the foam. And where it's venting out on the other side of this cap, you've got great cell structure all the way down. It's on the side of the part, guys. I mean, if you don't see it, that's okay. You see the waves? Is that the very bottom of it? Yeah, if you kind of look at that, you see the waves, and the bottom of it, if you're looking at it like I am, the bottom of it, of the cap, is right there. You see the waves? Now, if you rotate that cap, that's what the vent's doing. It's pushing up on that gas. But if you rotate the cap on the other side, it's just solid foam. Like that. It's just solid foam. There's no waves, nothing's going on there, and that's venting. So if you want to foam, vent that mold as much as you can, because you're actually going to go in quicker than you normally mold. I mean, anybody can just, squeeze and squirt, push it in, fill it out, that's fine. But when you want to add foam, you want to get it in really quick. And better vents help if you're injecting faster, typically when you're burning, that means your vents are bad. And then you have to slow your velocity down, and all of a sudden the burn goes away. Well, the reason that is it's not venting well.
Another question. Obviously, processors, some prefer liquid, some prefer pellet. Maybe you could touch on how the foaming agent is offered.
Say
What
that
form?
again. I can't hear you.
Sorry, the forklift.
That's all right.
In what forms is the foaming agent available?
Right. So we have powders. Powder foams work really well in like rotational molding. Some people prefer it in extrusion. We have pellet form. We've got different sizes of bubbles in that pellet form, and we have the standard 5811. 5767 is like a fine cell. 6295 is an extra fine cell, and then the 6265, which is our microfine cell. Different bubble sizes all the way down for different applications. And we do have a liquid microfine cell. We have it both in exothermics and endothermics. Now I gotta be honest with you, man. I've run pellets in extrusion. I've had good performance of the pellets, but I can tell you, we've got a major extruder does a lot of sheet, and they'll never go back to pellets. That liquid performs extremely well. I mean, all the way out in the sheet. It's just very consistent. So yeah, I mean, we can handle just about and we do. We offer pumps that we got a partner of ours that sells pumps, and we can hook you up with him, and he can get you a great pump for and whether it's injection molding, extrusion blow, whatever it is, we got liquid for it.
Another question came in. Do the foaming agents have any strong effect on colored parts?
Actually, it'll actually make colored parts darker sometimes. When you got a lot of people have dispersion issues with color and things like that, but you add a little bit of foam with that, and it'll disperse that color extremely well. I mean, even with a GP screw without a mixing screw, I mean, it does a very good job of mixing it, only because it drops that viscosity down to where it mixes really well. I've had colors actually look better with foam, the aesthetic end. Non-aesthetic, of course, the red gets a silver streak, and it changes the color. But you know, we all know it's red, but that is a fully foamed part. Fully foamed part. So it'll affect the color in that way. As far as aesthetic wise, I mean, if you do it cosmetically, again, you won't even know there's foam in it. And it'll be the same color as always.
Can you combine the color and the foam?
Yes, we can. We call it our one pellet solution. And we do this with a lot of companies that run thick wall parts, and they need aesthetic high gloss surfaces, and they, you know, on thicker parts, I believe they're polypropylene. On thicker parts, if you have too much foam in there, the cycles go long because they really have to freeze it off. Otherwise, they try to come out too fast, and they'll start bubbling up and expanding in the thicker sections. So it's really tough to meter a 0.2% foam in a part with an auger feeder. But if we add it to a 2% color, now you're dispersing that 0.25% foam or 0.2% foam at 2% let down in a color. So you get complete dispersion on lower percentages. And it's a cost savings too, because you're paying for two different products. We can give you one.
Cool. Going back to the cups, somebody asked if you have cups, is it safe to assume FDA certified
Yes.
on some of these foaming agents?
Yes, all the cups, everything, endothermics, all of our endothermics are FDA certs. We have just about every cert there is on it. Very, very, very good FDA.
Obviously, foaming agents require great technical support. What are you guys doing right now during all the COVID shutdown stuff to help with that?
Well, I do a lot of FaceTime, WhatsApp, Skype. I do trials like that, and I'm batting pretty good at that because I get to see what the machine is doing. A lot of people, they look at the screen, they look at the, you know, which the PC units are awesome. I'm kind of old school. I'll go back and actually look at the screw, watch it get back. A lot of times I'll count how long it's back, you know, and I may be off a half a second or something like that. But we do a lot of remote tests. And if it's within a drive for me and you guys are accepting people, I would like to come out and, of course, mask up. You know, I take all my precautions, and I've been to multiple trials so far, and have been successful, and I'm still here, man. So I take all the precautions necessary for me. It's important for me because I'm not young anymore.
I think this is one of the last few questions that have come in. If anybody wants to keep pouring them in, and we can even open it up. Again, he's not going to be able to hear you audibly, but maybe he can through the computer. We'd like to encourage more interaction, which we already have been. So thank you, everybody. But one of the last few questions, does foam help or hurt paintability of parts or even welding? Sure.
So when you're talking about foaming agents, you're talking about exothermics, endothermics. Exothermics, whether it's injection molded or extrusion, they have to degas. And exothermics are notorious for slow degassing. I mean, I've molded parts that took 2 weeks before they could paint them. Took 2 weeks before they could put a simple label on it. Because if they didn't, a day or two later, it'll bubble up. Endothermics degas almost immediately. So within an hour, you can paint them. You don't have any problems with degassing. It degasses extremely fast. And that's why endothermics typically don't work that good in the extrusion profile, because they degas too quickly, they cool too quickly, and they don't hold profile as well as an exothermic. So Yeah, I mean, big difference there, but endothermics, you're pretty safe to do whatever you want to. Hot stamp, paint, do whatever you want to do with them.
Awesome. Another one came in. Structural foam was mentioned, but never really discussed past your introduction. What's
Sure.
the difference from parts with foam to structural foam?
Okay, so you have structural foam in maybe a high pressure machine that you're foaming apart. That's a structural foam. It's a low pressure process in a high pressure machine. They have low pressure structural foam machines. They're like they have one nozzle, they have an extruder, and they have like an accumulator, what people call an injector. These are on smaller machines. And then you have the big multi-nozzle structural foam machines. And I got to tell you about multi-nozzle structural foam because I've done just a lot of that, and I've learned a whole lot. I don't ever recommend not using nitrogen in a multi-nozzle structural foam machine. I don't recommend because it's cheap, you know. So, but I do recommend a combination of our 5811 around 0.5% to 1%. With nitrogen. That nitrogen is a physical gas, so it will create voids in your part, and the voids, most of them are at infill, but you'll get voids everywhere in the part, and the voids will move around. It won't be consistent. By adding an endothermic, like our 5811 at 0.5%, what that gives you is the opportunity to bring down that nitrogen, so it takes some of that physical gas out, and it complements the endothermic, which if you got a void like so, or even like so, and you add that chemical foam, now that void turns into a tiny little void because the foaming agent's expanding in those voids. So if you use too much nitrogen when you're adding chemical foam, the nitrogen will overpower it. So you want a nice balance between the two. But if you got too much nitrogen, you're just throwing away the foam. And I've always recommended in structural foam multi-nozzle a minimum of 0.5%. And everywhere I've gone, and maybe there's somebody out there that can show me otherwise, but everybody seems to think the 0.3 is the way to go. Well, for me, if you're at 1200 PSI or 1300 PSI or even higher and running 0.3%, you might as well throw that money out the door, because that 0.3 to me isn't doing anything for you. Now, if you're going to run 0.3, you want to make sure you drop that nitrogen down and until you start to go short, and then just bump it back up a little bit. That way you get a balance between 0.3 and whatever the nitrogen is. But I always recommend 0.5. And the reason you think 0.2% in that kind of business is a lot of money, by the way. But 0.2% in a 120 plus cc per gram gas, that's a lot of gas. And when you're at 1200, 1300 at 0.5, you'll end up being around 1,000, 900, maybe 800 psi, which means you've got the nitrogen down, your voids are not near going to be as bad, and that foam is really, I mean, you're adding over 60 cc's per gram of gas at 0.5%, which is almost a typical foaming agent at 1%. So you're adding a lot of endothermic foaming agent in there that's really going to do a good job. Plus, the endothermics change that viscosity of the screw in the screw before it gets to the nitrogen valve. And what that means is you don't have to blow as much nitrogen in it to get that material, the viscosity to change in that material, because the material is already changed. The viscosity is already dropped. And you can bring those temperatures down as well. So I don't ever recommend, in structural foam multi-nozzle, I recommend nitrogen with chemical. I never recommend nitrogen by itself, because nitrogen can control how fast you run that part. Because if you try to run it too fast, or if you're pushing a bunch of nitrogen in there and you've got a fairly long cycle and the parts come out looking great, you may run into something we call post-blow, which means you can put them on a truck, take them down to Florida, set for a week, and they start pulling them off, and they got blisters all over them. That's what I call post-blow. What I call blister is when it comes right out of the mold, and you got blisters on them. And nitrogen is that's all nitrogen. So if you can get the nitrogen down, means you can run faster without blister and without post-blow.
Keeping on topic with nitrogen, in order to get a density reduction of about 50% in the TPO TPE, do you need nitrogen?
In structural foam multi-nozzle or a structural foam machine? Or you just use the nitrogen as a gas assist type thing?
That's a good question. I'll let that gentleman type his response to that. And while we wait for that, do you have any experience in plastic pallets? In this case, we need structural resistance.
I got a ton of knowledge in plastic pallets. Done a lot of plastics. Yeah, plastic pallets, right. And they're either done injection molding, which, you know, I've seen injection molded pallets, but I think the vast majority of them are structural foam multi-nozzles. And chemical foaming agent with nitrogen, or even straight chemical. I've had an opportunity where I foamed a real thick pallet. They were using nitrogen and 0.5% chemical, but there was so much mass in this pallet that the chemical really didn't help a whole lot. But it did a little, but not as much as I would have liked it to. So I said, all right, because they were really worried about that cycle. So I said, all right, we're going to drop 2% chemical foam, shut the nitrogen off. We dropped 40 seconds out of the cycle and over a quarter pound of weight out of the part. So when you're running a pallet with nitrogen, always add chemical because it's going to make that pallet much stronger. The structural integrity is going to go way up. I don't know if you've ever seen a pallet where you bump it with a forklift and it breaks a corner off and there's a big hole in it. Well, that's too much nitrogen. And the reason they add all that nitrogen is they're trying to bring down the weight. But adding foam will take up where that nitrogen was. You bring the nitrogen down to where you can run faster cycles. You can improve the structural integrity and even pull more weight out of the part. It's at a faster cycle, that is. The deal with structural foam multi-nozzle is people, you know, structural foam is not taught in schools. It's not taught, it's really not taught anywhere. I try to teach foaming agent to help the guys understand what that foam is doing in their process and how to control it the best they can, right? And I've been doing a long time, and I've failed a lot, and I've learned a lot. And when I go in to do a foam trial, I like to educate the process engineers or process techs, and believe me, I educate all of them on how to foam parts, how to optimize that foam to get the best out of that foam. To where, because that is a cost, especially in multi-nozzle structural foam. That foaming agent's a cost, and that affects the bottom line. So it's typically up to me to go in, adjust the process to where they're actually making, even though they're adding 0.2 of a pound of foam, they're actually saving more money than they were at 0.3 and with 0.2 more. So their cost savings is even greater. So I do educate people, and it gets, again, it's been taught from generation to generation, and some of the stuff I read online I really don't agree with. And what I talk about, gentlemen, ladies and gentlemen, is things that I've done. It's very little that I talk about is theory. I've done so much foaming and so many different materials that I speak to what I've done, what I've seen. Just kind of how I roll.
I had another question coming in specific to the plastic caps.
Yep.
Which is better, the You mentioned the 5811 or the 6265.
The 6265, because that's our microfine cell. The 5811 is just way too aggressive for that application, for that thin a wall. So the 6265 is the best product for that. And if you have the velocity, I don't recommend going over 1%, because if you start going over, because in a cap, you can run 1% and just have a beautiful cap. Surface is class A, no splay at all, just loads of foam in the cap. But if you go to like 1.5%, you may get a little bit more, but not enough to just for that 0.5%. It won't justify that 0.5%. So I usually stick at 1% because you get the best for the money that you spend, the best results. It helps your margin much better when you're 1% instead of 1.5%, or even 1.25% for that matter. Oh. Hey, look, I just want to mention a thing to you all too, is as I said before, all applications are different. You know, we may have to change the process for this application because of, you know, screw design or length of barrel or flow length or anything like that. We may have to make different changes for that, but that's why we want to be involved with your processes, with your tech team, to get a better understanding. You know, if you want to talk to us offline here and go through a specific application, you can send us a part. If you need an NDS, we're happy to do that. But you can send me a part. I can take a look at the part and evaluate the part just as it is. And then we can go over the process, what the machine capabilities are, what's your targets, because we need to know if there's an impact requirement. We need to know at that point, do we go after maximum density, or do we take that down a little bit and keep everything within spec? So yeah, we want to be involved, because I might make adjustments over here, but over here I won't, because there's a whole different animal. So definitely reach out to us offline if you want to have a Zoom meeting with you and your team about a specific material, application, extrusion blow. These are extrusion blow molded applications, and they're just amazing. But if you need you know, more personalized contact to kind of customize your process and your application, let us know, because we feel like, you know, we feel like we're the best in the business, to be honest with you. And I like to be hands-on. I like to be fully involved in it, so that every step of the way, so that you see success. And, you know, if you see success, we see it as well. So that's how we operate. We have other products, you know, we got the Purge and the EcoPro. Our tech department, we have people that are very technical, that are hands-on guys, and we're all there, you know, as our technical team. Me and the foam, I want to be there to make sure that everything is done, and if there is any changes to be made, I can at least see the part and say, now wait a minute, we need to make this adjustment. And then I always explain why I make a recommendation, why I make a change in anything. I help them to learn what the foam is. And a lot of times, more than not, I can go and do a trial, and with that knowledge, these young men, you know, process engineers, process techs, if they've got another application, they can go and walk right over and start working on it.
We did have a couple more, and one going back to the TPOs and TPEs, asking about needing nitrogen to get a density reduction of 50% in TPO, TPE. It's actually for injection, for making it softer, goal of compression, deflection, and they're trying to make it more resilient.
Yeah. Well, I mean, if resiliency would probably be lean towards the foam. The gas assist or nitrogen, you know, the wearability, I mean, I don't think it'll last as long, you know, as a product, but I think with gas assist, it may be a little bit, you know, softer, you know, if it's like a donut or like a wheel, it'll, like a tire, right? I mean, it'll sink a little bit. Foam will give it a spongy feel too, but I think the foam will actually perform better as far as longevity and that. But again, I'd sure like a crack at that, just for me, because I've never been, you know, I've never foamed anything like that. I've foamed TPE, but not in that kind of application or that kind of part that they're looking for. But I'd sure like to be involved in that, and I'd sure like to be challenged, because I know I'll learn a lot in that.
On injection,
So
does it need
whenever
a
you
special
use
mold
foaming agent, right,
or
and
a
we
special
tout our
machine?
foot, you know, to reduce your footprint. When you drop them barrel temperatures, you're saving energy. When it's low pressure, you're saving energy. It's when we did a Sumitomo Demag test. We did 2 tests. One was this living hinge cap, and if you need information on that, we actually did a C-scan on this. The hinge, there's no gas in it at all, and I'd be happy to explain why that is. But these caps, we dropped the energy to 10% on the caps, and then we did like a door hinge thing, and it was over around 18%. Energy, 18% energy reduction. So whenever you're dropping barrel temperatures, you're saving energy, bottom line. If you're using low pressure application in an injection molding process, you're saving energy. So, I mean, I think one extrusion trial I did, I bet I was, with the kind of heat we took out, I bet it was close to 30% energy reduction just in that one machine. That's how much heat, we just took a ton of heat out of that.
We have another question before opening it up even further. For unfilled nylon in an injection molding application, 1 inch thick part, what do you think is the maximum density reduction that can be achieved?
So I think you can hit about, with the 71896, really, you know, just not really changing a lot. You could probably hit about 3.5%, 4%. Now then, if you want to really drop the weights, you inject it fast. The faster you inject it, the lighter it gets. If you're injecting, if your fill time is a 3-second fill time, and you can get that down to 1, you're going to be super light. And again, you take material out, you always go short, and you just, you know, if you up the foam, you always want to go short, and you want to fill it, add a little more material, maximum velocity, and add material till you're just full, and that's as much as you're going to get out of it. And you could hit 10 plus, maybe even more on an inch thick part. That's a lot of weight you can pull out of that. Just depends on how fast you can inject it.